Yes, I have a and they can only so when I got up, it was like 5. So like my laptop.
Good afternoon. So after last class, someone asked me a question to say, what is this guy? So first, we know beta is what? Beta is A1, A2, B, right? Beta is a vector, is a parameter vector, all right? And then what is beta? This is a L2 norm, right? This is a A1 square plus A2 square plus B square. This is a length, the magnitude of beta. Then what is this beta square? Then raised to power 2. That is A1 square plus A2 square plus B square. Okay, is that clear? Right. So I should write this at the beginning. Okay. So we discussed why we need to have training and testing. Right? You need training data to train a model, and in order to replicate or try to evaluate what's the performance of this model in real-world scenario, we need to test it using unseen data. So this is why we need to partition data into training and testing. Again, as I mentioned, in this class, we will try to, without make things more complicated, we just say training and testing. But in a more regularized real-world scenario, you like to introduce another set of data which call validation. You have training, validation, and testing. So in that case, the testing will be the true testing. Okay, so you will train your model and then using validation data to select, let's say, hyperparameter, right? You decide what is lambda, those things. After you converge, after you say, hey, this is a best experiment, then probably you want to apply the model to the test data. Yeah. All right. I just remind. I think that we probably still need the mask in the class. Yeah. Sorry about that. Yeah. Thank you. I think that the school still required it, so I just try to help to enforce this protocol. Yeah. So the next is we call cross-validation. There's some very famous scenario called k-fold cross-validation. It's a very smart idea. What we are trying to do there is, let's say you have a data set, okay, and you try to partition them into multiple fold. The typical number of fold we usually do is something like 3-fold, 5-fold, 10-fold. Okay, 5-fold is one of the very common scenario. So you partition your data into 5 different partitions, and then you try to keep one of the partition as your testing, and using the remaining 4 as your training. You're training your model using your 4 partition and test on the remaining one. Okay. After that, you try to repeat this, and you try to using another partition as your testing, and using the remaining for training, and then repeat this for 5 times. So in this way, the advantage is you have make use of your training data, right? And you have evaluate or do whatever evaluation or selection by maximize your data. You have. Otherwise, if you only keep training and testing, you are try your luck to say what are the data fall into training or data fall into testing, right? Because if you do not have understanding about your data, it's likely maybe some of situations, let's say, doesn't be covered in your training, only appear in your testing. So you always get a little bit permissive result or something like that. Yeah, but using this way, you have make full use of all your data. All right. So the concept is very simple. And to one extreme, it will become a leave one out cross-validation. What does that mean? That means each time you only leave one sample out as your testing and using everything else for your training, right? This is called leave one out cross-validation. But of course, this is a each time you make full use of your training data, because almost using everybody to train the model. But the drawback is, of course, you need to do a lot of more test effort, right? Because it's a lot of training and testing. Okay, so after you do this cross validation, you can each time you will have a model performance, a model MSE, right? You can take an average of them all as your final understanding about, let's say, a hyperparameter selection, right? This is a much more fanciful, reliable way. For example, this is how we use cross validation for model selection. So now we want to determine the right value of lambda. Okay, then we want to test a wide range of lambda, typically log scale. Like I think I mentioned this part. Lambda, actually, there's no range constraint for lambda. Lambda, you can take 1, 1.2, 1.3. There's nothing prevent you from doing that, but it's not worthy to try it every single values. So usually we will try to doing this kind of log scale. We put like 0.01, 0.1, 1, 10, this kind of. Every time you try to test a value, you start with some maybe pretty large value, maybe 1,000, 10,000. Then use every time you reduce by 10 and see how it works, right? And so if we are using cross-validation to pick what is the best lambda, you can do, let's say, decide lambda equal to 0.01, and you do a 5-fold cross-validation. You take the average. So this will give you an indication to say, or give you a very honest or very to your best of knowledge measure to say what is the MSE, what is the performance of this lambda equal to 0.01. Okay, so then you do 0.1. I decide to pick another lambda value as 0.1, and I'm doing another 5-fold, take the average, then I will see, hey, what is the performance? And so on. You pick lambda equal to 1, lambda equal to 10. Then you choose lambda equal to lambda star, which is basically the best of all cases. Then you say, hey, this is my lambda. So I hope from this example, you also start to see my point to say why we probably need a validation. The test that we call here actually is a kind of validation, because the test data here is part of your training, right? It doesn't serve the purpose to say, I want to test my model in the real world unseen scenario. So for that purpose, you need another set of data, which you never see. You never see during your training. Okay, because now you say, I choose lambda, which have the best performance. That means you have seen all the data. You have to use the data to select the model. Okay, but again, as I mentioned, in this class, let's say testing and training we're using this way. But I just hope you be aware. There's another concept called validation. Okay, called validation data set. Okay, it's not required. It's just nice to know in this class. Okay. Okay, there's another super small cross-validation example. We have let's assume that makes things simple. We have only 3 data sets. with a single feature X and a target value Y. So during the data collection, you will collect X, Y. Okay, let's assume we have 3 data sets collected. This is a second. Okay, and then you will try to find a linear regression model Y equal to X plus B, because we only have one input feature. So we have only one A, and then B is our the bias term. Yeah, sometimes we call this intercept. Sometimes we call this bias term. If you see certain papers to talk about the bias term, then that is referred to B. And the corresponding regularization. Sorry, I a little bit fast today because I want to match the exam schedule. So hopefully we still have one topic about the natural language processing, NLP, which I hope I will start talk about today. And our goal is to cover here the object and the classes, and that one is optional. We will really depends on how fast we can proceed. Then I will talk synchronized with the other section. The other 2 sections, we are more or less around this. We are all talking about the cross-validation example this class. So we are very synchronized. Yeah. But we will try to push towards the object and class. If we can't, then we will not put that in the exam. Yeah. So, but definitely the text part, which will be part of the exam. So I try to reach that part. Yeah. So then if we are using a ridge model, again, what is ridge model? Ridge model is by a ridge regression, right? By adding a squared version of L2 norm of your beta, right? By adding lambda. I just mentioned this by adding this term to your mean square error. You want to minimize this. So this is your ridge regression by adding another regularizer. If you forgot what is a ridge regression, why we need a ridge regression, try to go back to the these pictures. By playing the lambda, you will see by adding this term, do able to prevent some kind of overfitting. All right. So now we are doing a 3-fold, and we want to test out lambda equal to. So basically, try to test this lambda value equal to 0, 0.1, and 1. See which one is the best. Okay. Yeah, it's a, oh, okay. So I think that probably I made a mistake in my example. In my example, I said the beta is to put the B into the regularizer. Yeah. So actually, the B should not be part of the regularizer. So this is the mistake I just made. Is at beginning here. Sorry. Yep. So this B should not be here. All right. Okay. So we only regularize about the A part. Apologize for the mistake. Okay. So what we, yeah. So here, because to do 3-fold, again, we need to repeat the whole process 3 times, right? You partition your data into 3 chunks. Then you take one of them as your testing, then using remaining 2 to train your model, right? So then you probably first time you take the chunk 3 as your testing. Then in the second round, you will take the chunk 2 as your testing, and the first and the third as your training. Then you take the first chunk as your testing, then using the second 2 as your training. So you repeat this 3 times. Okay, so let's assume this is a fold 2. Fold 2 probably that means I don't know the order, but probably it means maybe using first and third as your training, the second for your testing. So then for that one, we will try to during each fold, you will try to set a lambda. You will say, okay, the current lambda equal to 0. Then plug in the formula. If you does this record anything to you? If this doesn't recall anything to you, you need to refer to the ridge regression, the closed form solution to that. Okay. So remember, how do we solve the beta, the vector beta for ridge regression, right? We're using X transpose multiplied with X plus lambda multiplied with the identity matrix. Remember, start recall. And then you take an inverse of this, then you multiply with X transpose, right? Remember, start recall the formula. Yeah. So this is as you can see, all those will be performed in the using the NumPy in the Python. We have covered all this part. So this will give you a calculation. Since you know A, you know X, you know Y, right? So you can use this to compute out some result. All right. Same thing, you can repeat the same thing by choose a different lambda. And each time after you decide that, then you recall the formula. This is the one inside the parenthesis, and then you take the inverse, then you multiply with this, then you multiply with Y. Again, you will get your regression result. And take this, compare with your ground truth, and see what is a mean square error there. And that will be your error term. Then you start to do this for each lambda, then decide what is a limit, what is the smallest error. All right. Is there any questions for this part? I hope this procedure is pretty straightforward. Yeah. So go back to read a little bit more about to see if there's anything, you can come back to me. But I believe if you refer to the closed form formula, those things are pretty straightforward. And also, this is very good to tell you how to do this actual step in the. If you ask to write linear regression, how do you code it in Python? But of course, as I shown you, if you do the sklearn, you don't even need to do the actual fitting, right? You just call regression.fit data, then you get your parameter. But this is try to show you how to exactly do that, to open the box to show you the inside. Okay. So done with this. I want to very quickly to show you the sklearn toolbox. Okay. So again, at the beginning, we try to, oh, sorry, I can't. So first we import all the sklearn, like the corresponding regression, training test, then R squared score. As you can see, all those functions we have covered. They all have a corresponding functions in the sklearn package. Okay. So first, let's start to load some data. So sklearn has some diabetes pre-existing data. You can load them, and now we just take only probably the first 20 of them because I believe that is probably data set with a lot of entries. We take the first 20, and only we take one of the feature as our training data. As you can see here, sklearn has a training testing, and then you try to split your data into X-train, Y-train, X-test, Y-test. You try to split the data into training and testing. And the training and testing data, usually we they both should have the ground truth, right? Because the test data is used for to evaluate your model performance, all right? So you need to know the ground truth. Otherwise, how do you tell from the testing data how good is your performance, right? So which is reason you know Y-test. Y-test is a ground truth associated with your test, all right? So then you, okay, we just print out a few things. We can see this is we print the first 5 X-train. You can see this is what we have. Then again, I think that we have see this. You just call the linear regression, and you allow the bias turn, and then you try to fit X trend and Y trend. You are fitting your model using training data. So no testing data here, just train from the training data. And then you can print, as I can see, now you have your coefficient. The coefficient is all the A's, and then you have the intercept, your B's. In the cross-validation example, we just see we are opened up the box. If you don't want to call this fit, right? You need to using this X transpose X. Those are inverse. Then you're using this closed form solution to solve for the A and B. Okay. And then you can using the regression model to predict. The predict is to say I plug in the X test. I plug in my testing data and see I get some of the prediction. And then because I know Y test, I know the ground truth associated with those test data. So I can evaluate how far away your predicted value is different from my actual test labels or the ground truth associated with test. All right. So now we are ready to do evaluate the mean square. You can directly call the mean square error. You can plug in the Y test and the Y predict test. One is the ground truth, Y is produced by your model. And of course, you can also compute the R square score. R square score is capture the mean square error. At the same time, it also take into account of your variance. So it's a more comprehensive measure. So as you can see here, so you have a pretty big mean square error, okay? And also the worst scenario is you have a negative R square score. As we talk in the class, we hope we are saying 0 means really bad, 1 means really good. So now we have something even worse than 0. That means really, really bad. Okay, because it's okay to have negative, because the 0, that means you do as good as your average of Y. So this means we are do even worse than our average. So instead of building a regression, you should just tell me the average of your Y is better than what you are doing. So the reason is because we only have a very small amount of data. We are using only 20 of them. I forgot the actual number. Yeah, we're only using 20 samples. So it's a we haven't get a very good model at all. Yeah. All right, so if we plot out, as you can see, it's not very good. Also remember, we didn't normalize anything. Yeah. So normalization is especially important when we want to read a little bit the information from the weight. As I mentioned, if you do not normalize your data, you can't using the weight to tell anything, right? If you normalize your data, you assume, okay, all the features fall into our zero mean and standard one duration Gaussian. Then I say if A1 is larger than A2, then I will say, hey, the first feature is more important because a small change in X1 will cause more change than X2 to my target value. So that means the first feature play more important role. So now let's normalize X. Is try to take the mean, you take the standard deviation, and also you can take the mean and standard deviation of Y. Then you try to do something like when you compute your Z-score, this is exactly, you take away the mean and divide by standard deviation. But as I mentioned, usually the normalized the X is pretty common, but normalized Y is a kind of optional. Yeah, optional. If you are doing this kind of simple linear equation, normalized Y is not always required. But in this class, since we in the slides we mentioned normalized X and Y, so probably we assume you will normalize both. And then after you normalize, then you fit, and you fit a regression model, then you do a test, then you found your error is huge, even bad, even worse than before. What happens? Because what? Because you didn't normalize your testing data, right? Because once you normalize your training data, you need to normalize your testing data. So now I go ahead to also normalize my testing data. Then I do the plugging into the formula again. I get back my mean square error as before. Okay. So this is pretty much. I believe we will release this the Jupyter notebook. So take a look. Is there any questions so far? When I go through, does this cause any concern or any place which feels mysterious? Are we fine? Okay. Very good. I love the linear regression, so I hope to continue on and on, but I have to move on to the, so I need to fast to finish this part. And now let's see, any questions about linear regression? So probably I can take one last question before I move to the text part. So I hope you feel excited about this linear regression. It's a very fun topic. So the cross-validation concept is okay, right? So I assume it's pretty straightforward. You just basically try to make full use of data. But if you, in case you have any questions, you can send me emails or ask me after the class. Okay. So now let's move to another very important topic, which is a text data analysis. Okay. So in real world, I think that the probably three most popular data analysis is text, vision, and then the speech. Okay, so among these three, also the text and the vision receive more attention now. And nowadays, the text part is especially after we everybody deploy, especially those big industry leaders, they apply the deep learning method using huge amount of data. You just imagine how much data Facebook have, how much data Google have. So they make use of those huge amount of data. They try to come out with a lot of recent breakthrough to really push the text recognition. If you use like me using like a Google Translator in the past several years, I'm sure you start to see those translation quality improves dramatically, right? Yeah, so, but here we are talking about some of the more fundamental tools to text analysis, but the underlying philosophy is more or less, even those things are simple, much simpler than what people are doing today, but this captures some very essential, the core idea. Okay. So why we need to do text analysis? Of course, there's many purpose. One of the most simple purpose is I want to classify the topic of my text, which is very easy to understand, right? I give you an article. Can you tell me is relate to sports or relate to entertainment or relates to music or how can you do that? Also, you see an article. Is this article give you some try to talk about some negative opinion or some positive opinion? You just agree, disagree on what you can imagine how useful are those text analysis, right? So for example, now there's like a Twitter, there's so many articles. So if a lot of time you rely on automatic text analysis in order to try to understand those things. Yeah. All right. How to do that? Actually, the basic idea is very simple. It's counting frequency. Okay. You can, of course, I mentioned this as a very simple idea, but you can do this in a more fancy ways, right? This we will cover here is talking about just counting frequency. For example, I get an article, then I will say, I will just see which words appeared most. Of course, I don't count like M, is, are, those words. We call that stop words. We'll remove them because those words anyway, well, this, that, it doesn't contain much information. But I will try to capture those words which does not belong to the stop word. Then I will just say, hey, which words appeared most often? And that should give you a very good description about your article. Okay, so that is a basic idea among the text representation. Even today, we are using a deep learning. We are doing a more fancy representation, but still, it ends up with another fancy way. For example, it will more counting, let's say, call occurrence. It will try to see some words appeared more close together or more frequently appear in the same article. They will share similar representation. So basically, adding a little bit more fancy dimension into the picture, but the still is a kind of counting frequency. That is the basic idea. Okay. In order to counting the frequency, we need to chop your article into some unit. We can start to counting, right? Because the article, they can be of any length, some short, some long, and we need a meaningful way to have the atomic basic unit to start to say, hey, I need to count frequencies. Tell me what will be the unit, right? So this is to achieve this, we have a basic idea called n-gram. The n-gram is to break a sentence into overlapping subsequence of length n. Okay. So the n here is a variable. You can decide the actual value. For example, you can say n equal to 1. You have unigram, n equal to 2. You have bigram, n equal to 3. You have trigram. For example, we say I saw a cat. If I want to do word-based 3-gram, I will have I saw a cat. As you can see it's overlapping. Each time I move by one word, then I preserve 3 words as my unit. Do you see that? Right? So of course you can also choose to do character-based 3-gram. Then each time you will take 3 characters, then you move by 1 character. So you can see now you obtain another level of the represent of the unit, right? Any confusion about the n-gram concept? Yes.
So you have a comma, like let's say we have a comma at the end of saw.
Right.
Would it be included?
So yeah, very, very good question. I think that it's first of all, maybe there's some applications do require you have a comma. Maybe you want to generate some article, you want to, you know, some of the article you read today in the newspaper is machine generated. Yeah. So, but to understand in some applications, for example, like the application we are talking now, you just try to represent an article as a representation and classify what the topic. Those commas doesn't contribute. So usually we will remove those commas, full stop, those things. Yeah. So we will only have the words remain. Yeah. And also, as you can see now, we are preserving the order inside each unit. But across unit, we no longer care about the order. So now the order across different those each, I don't know what's the word I should call this. Each unit, between those units, there's no orders. We do not. So which is reason we call them a bag of word model. So it's like a bag, right? A bag, you put things in a bag. There's no order. It's a bag of words. It's actually is a more accurate is we should say bag of n-grams. Okay. So now you start to see the reason why we have unigram, bigram, 3-gram, trigram, because you are increase the number of n, you preserve longer order across different words, but to a certain extent, because once you include too many words in one n-gram, then that may complicate things. For example, if you put 100 words in you get 0 count for a frequency, right? Because that is not very useful, right? So you have to try to decide a balance, because when you're using a smaller n, you are losing the cross-word related information. You are just throw them away. So this is a kind of trade-off in design. All right. So the reason, again, we come back to why we want to do this anyway, because we want to counting frequency. We want to see what are the most frequent appeared item in an article. Okay. So if the same n-gram appear multiple times in a string, that indicate a high frequency. Okay. So for example, if I have piece of raw text, it's a puppy and it is extremely cute. Okay. So to represent this, remember, as I mentioned, why you need a linear algebra, you need a matrix. You need a matrix is because a lot of your data are in matrix form. But you say, hey, this is a text. How do I obtain my matrix form? So now here comes to the story. So I have a raw text. I want to convert this into a vector. I want to have a feature vector to represent this piece of the text. How to do that? First of all, very simple. Actually, you just say, hey, this is my vocabulary. This is my common vocabulary. Let's say this is a 500 most used word in my dictionary. I will say, okay, so I will make that vector to be a 500 dimension. And then for each of the words in my dictionary, I will start to put how many times your words appeared in your text. Does that give me a very simple or maybe a little bit simple-minded version of the representation? But still, you have a way now you convert a piece of text into a vector, right? So probably now you can start to build your linear regression, right? Do you see my my trick here? This is actually very, very important representation. Yeah, a lot of time we do feel good by stay at this simple representation. It's very simple because you just has a list of vocabulary, then you just counting the frequency. Then that is a unique signature to represent a piece of article. All right. So then you can start to build your linear regression. Later you will see a classification model. All right. For things which does not appear in your article, you just put 0. Of course, in this bag of word vector is a little bit too naive because I can see it, they, and. Those things are still be there. And obviously those things will need to be removed because every article have it that, right? It doesn't bring any additional information. All right. Any question about the bag of word concept? It's a very simple but very powerful concept. Yes, question. This is frequency. I have one it, two it, right? Puppy appeared once. So this is you're counting the frequency in your text. All right. Yes, so we are okay so far, right? So now one of the tasks, as I mentioned, is to classify your article, classify them into topics, or even identify what language is Spanish, is English. There's many applications. Okay. So one thing we can do is we can consider to do that. We consider the n-gram characters contained in the document. So document written in a particular language. So this is a more focus on a language classification, right? They tend to have a very similar n-gram frequency. So this is just try to give you a very quick example to say why the frequency is useful. For example, you want to tell let's say I don't know English, I don't know Spanish, but you give me an article. I don't know what language is that, but what I can do is I can compute the frequency of those n-grams, and then I just match with n-gram signature of different language. Then I can tell, hey, this is a Spanish by matching the closest the frequency histogram. All right. So for example, this is if we build a histogram of n-gram, then we can basically you treat each different n-gram across the document a separate bucket. So this is what we are talking about. That. So assume you are building your most frequent the n-gram appeared in a language, and you try to build a histogram of those. Then this is a French, this Spanish, this English. Then this is a mysterious document. Then I will try to tell what language is inside this mysterious document. Then what to do is I just try to compute probably the mean square error to each of these histogram. Then I pick the one with the minimal distance. Then I will say probably this is a Spanish. This is also useful as a, let's say, as a first step in tailored article. I think that a lot of times now, if you load a picture in a language you are not default, probably the browser will ask you, hey, do you like to auto translate your article right into English? So how do they tell what language this article comes from? Maybe there's more fancy ways, but at least this gives you one very simple way. Right? Okay. So how do we quantify the importance of n-gram in a document? So without reading more, give yourself a think. I will encourage you to think about how do you see, why you think, how do you decide the importance of n-gram in an article? Can you think about that? If you post a question, I ask you, hey, how can you tell me, is this words important words for this article? So a hint is at least you need to think about two things. Okay, think about that. Yeah. First, what? Obviously, frequency, right? These words need to keep repeating in an article, right? But there's another thing. There's another dimension which I haven't talked. I will talk probably in the next slides. Yeah, but can you think about that? What is the second reason or cause which make me think this word is important in this article? The second dimension will be these words will be very less frequent to appear in other articles, right? Do you see the point? If I say those words are so unique and so important, meaningful for an article, first, these words need to be really some major words in this article. And also, this words is not that popular words in other articles. So that means these words become a very unique description for this particular article. Okay, so this is a who points we will present next, how to evaluate how to represent or how to extract some signature of an article. Yeah, I see people need to leave, so probably I will dismiss in another 1 or 2 minutes. Yeah, so but if you have anything, feel free to leave early. So one possibility is counting the number of times occurs. It's a frequency, and the more frequency, obviously, more frequently occurring should be more important. For those common words like am, is, as, those things we call stop words, which will be first removed, okay? Because those words does not bring additional information. And there's another words is called, if you are particularly, let's say if you have articles, you know they are all belong, let's say, from a Disney company. They're talking about Disney. So in that one, then Disney in that collection doesn't bring any additional information because you know anyway, this is a topic about Disney. All right. So in that special case, the Disney will be also a word to be removed. So then we need to say how unique is the n-gram is across the document. This is we will carry on next class, but remember these 2 dimensions to measure the uniqueness. Okay, so okay, that's all for today. Thank you.